Chapter 5 Language of Chemistry. In previous classes, discussions about the symbols of elements and the formula of compounds helped in expressing their long names as shorthand notations, which forms the language of chemistry. In this class, students will develop the ability to derive the formula of compounds if symbols of elements of radicals forming the compound and the valencies are known. They will also be able to write chemical equations if the reactants and products and the symbols of formulae are known to them. Learning outcomes. After studying this chapter, students will be able to recall the symbols of different elements, derive the formula of compounds on the basis of valencies of elements and radicals, write chemical equation of a reaction, balance chemical equations by applying the law of conservation of mass. Important terms and their definitions. Symbol of an element. Symbol of an element signifies the name of the element and the atom of the element. Reactants. The substances that take part in the reactions are called reactants. Products. The substances that are formed as the result of reaction are called products. Precipitate. When two reactants react and product formed remains insoluble and settles as a solid, it is called a precipitate or PPT. Word equation. The description of a chemical reaction in words is called word equation. Introduction. Chemistry has its own language which consists of rules and conventions to help organize the representation of substances and portray the changes that they undergo at the atomic level. Every chemical entity has an identifier. For an element, it is the chemical symbol, while for a compound, it is the chemical formula. Matter undergoes changes and these changes are represented by chemical equations. Names and symbols of elements. The names of elements are derived from various sources. For example, some derive their names from Greek, some from Latin, some from the regions of discovery, some from the names of famous scientists, and so on. The International Union of Pure and Applied Chemistry (IUPAC) has therefore allocated a unique chemical symbol for each element. These symbols are accepted, understood, and used by scientists all over the world. How elements got their symbols. The symbols of most of the elements correspond to the first letter of their English names. For example, the symbol of hydrogen is H and that of carbon is C. When more than one element has the same initial letter in their names, for example, carbon, calcium, chlorine, and chromium, then the symbols have two letters. For example, the symbol of carbon is C, symbol of calcium is Ca, the symbol of chlorine is Cl, and the symbol for chromium is Cr. Similarly, the symbol of manganese is Mn, whereas symbol of magnesium is Mg. While writing these symbols, the first letter is always capital and the second is small. The symbols of some elements are derived from their original Latin names. For example, the Latin name of iron is ferrum, so its symbol is Fe. Similarly, the Latin name of gold is aurum, so its symbol is Au. In 1808, John Dalton, a scientist, tried to name the various elements based on these pictorial symbols. Some of Dalton's symbols are shown in figure 5.1. The use of these symbols was discarded by Berzelius and introduced the modern system of representing an atom of an element. Significance of the symbol of an element. Symbol of an element signifies name of the element, one atom of the element, a definite mass, atomic mass of the element. For example, the symbol C for carbon denotes the name of the element carbon, one atom of carbon, a definite mass of carbon, that is 12 atomic mass unit, 12 AMU. The names and symbols of some elements are given in the table below.
Names and symbols of some elements. One or two letters of the Latin name of an element.
Formulae of elements. A molecule of a noble gas, that is helium He, neon Ne, or argon Ar, contains only one atom of the element. Hence, the molecules of these elements are represented as Hene and Ar. These gases are said to be monoatomic. However, a molecule of hydrogen, nitrogen, oxygen, or chlorine contains two atoms of the element. They are diatomic and are represented as H2, N2, O2, and Cl2 respectively. A common example of a triatomic gas is ozone, O3. Atomicity. The number of atoms contained in a molecule of an element is called its atomicity. The atomicity of phosphorus is 4p4 and that of sulfur is 8s8.
Atomicities of some elements. Atomic masses of some common element.
Compounds. A compound is a pure substance formed by the two or more elements chemically combined in a fixed ratio by mass. For example, water H2O is a compound formed by two elements, hydrogen and oxygen, chemically combined in a fixed ratio of 1:8 by mass. Similarly, common salt sodium chloride NaCl is a compound formed by two elements, sodium and chloride. Ammonium chloride NH4Cl is a compound formed by three elements, nitrogen, hydrogen, and chloride. Compounds can be further divided into three classes: acids, bases, and salts on the basis of their properties. For example, sulfuric acid is an acid, sodium hydroxide is a base, whereas sodium sulfate is a salt. Formulae of compounds. The formula for compound formed by two elements is obtained by transposing the valencies. Suppose an element A has a valency Y and element B has a valency X, then the compound formed between A and B will have the formula AXBY. The subscripts should be divided by a common factor, if any. There are some exceptions like H2O2 hydrogen peroxide, in which the numeral subscripts are not divided by the common factor. In the following table, formulae of some common compounds are given below. Characteristics of compounds. Compounds are homogeneous in nature. They cannot be broken into their constituent elements by physical means. The physical and chemical properties of a compound are different from those of its constituent elements. Energy is absorbed or liberated during the formation of a compound. They have a fixed composition and a definite melting and boiling point.
Formulae of some common compounds.
Variable valency. In some elements, the valencies vary. Such elements are said to have variable valency. For example, iron has a variable valency of 2 as in FeCl2 and 3 as in FeCl3. To distinguish between them, FeCl2 is named iron 2 chloride and FeCl3 is named iron 3 chloride. This method of naming a compound is adopted if it contains an element with variable valency. Some elements with variable valencies. Hence, knowing the valencies, we can write the formula for the corresponding compounds. Copper 1 chloride, copper 2 chloride, iron 2 oxide, iron 3 oxide. World of atoms. By the experiments of Sir J. Thomson, Lord Rutherford, James Chadwick and others, it was proved that atoms are made up of still smaller particles, electrons, protons and neutrons. They are called subatomic or fundamental particles. The electron. An electron carries a negative electrical charge, which is considered as the unit of negative charge. It is extremely light, 1800 times lighter than the lightest of all atoms, therefore its mass is negligible. The proton. A proton carries a positive electrical charge, which is taken as the unit of positive charge. Its mass is the same as that of a hydrogen atom, that is 1 AMU. The neutron. A neutron carries no electrical charge. In other words, it is electrically neutron. So the name neutron. Its mass is almost the same as that of a proton, that is 1 AMU. The atomic mass unit, an atom is so light that one cannot weigh it on a balance. Scientists use the mass of the hydrogen atom as the standard for measuring the masses of other atoms. According to this scale, the mass of the hydrogen atom is 1 atomic mass unit, AMU. Isotopes. Some elements have atoms with different mass numbers. For example, chlorine, atomic number 17, has two types of atoms with mass numbers 35, 3517Cl and 37, 3717Cl. Such atoms are called isotopes. Ions. Electrically charged atoms are called ions. Positive ions are known as cations and negative ions are known as anions. Radicals. Ions are also called radicals. Na+, K+, Ca2+, etc. are positive radicals, whereas Cl-, O2-, S2-, etc. are negative radicals. There are certain groups of atoms that behave like single atoms. They have a valency and usually remain intact in a chemical reaction. They are called compound radicals. Such radicals also carry positive or negative charges. In the following table, some common compound radicals are given.
Some common compound radicals.
The formula of compounds containing radicals can also be written by transposing the valencies and dividing them by a common factor, if any. For example, the compound formed by Cu2+ and CO3 2- is CuCO3 and not Cu2 or CO3 2. Here valencies 2 have been divided by the common factor 2. In the following table, formula of some compounds have been mentioned.
The formulae of some compounds.
Organic and inorganic compounds. In olden days, the compounds obtained from living organisms, plants and animals were called organic compounds. For example, all carbon compounds except CO, CO2, carbonates and hydrogen carbonates. The compounds obtained from minerals were called inorganic compounds. For example, ion carbon compounds plus CO, CO2, carbonates and hydrogen. Chemical equation. A chemical equation is the symbolic representation of a chemical reaction using the symbols and the formulae of the substances involved in the reaction. In other words, a chemical reaction can be represented in the form of a chemical equation. Chemical equation. Let us understand it by an example. When magnesium ribbon is burnt in air or oxygen, it forms magnesium oxide. This description of the chemical reaction in the form of a sentence is quite long. It can be written in a shorter form. The simplest way of doing this is in the form of a word equation.
The word equation for the above reaction is given below. Magnesium plus oxygen reactants gives magnesium oxide product. A word equation shows the change of reactants to products through an arrow placed between them. The reactants are written on the left-hand side, LHS, with a plus sign between them, and the products are written on the right-hand side, RHS, with a plus sign between them. The arrowhead points towards the products and thus it shows the direction of the reaction. Steps involved in writing a chemical equation. Write the formula of reactants on the left side of the equation and the formula of the products on the right side of the equation. Mark the sign of an arrow between the reactants and products. If there are two or more reactants or products, insert plus sign between them. Write the reactants and products in molecular form only. Atomic forms are not stable. For example, if chlorine and hydrogen are involved in a chemical reaction, write them as Cl2 and H2 and not as 2Cl and 2H. Number of atoms of the reactants and products on both sides of the equation must be the same. In other words, the equation should be balanced. Solved examples. Example 5.1. Write chemical equation for the reaction. Magnesium burns in oxygen to give a white powder of magnesium oxide. Magnesium plus oxygen gives magnesium oxide. Steps. 1. Formula of the reactants MgO2. 2. Formula of the product MgO. 3. Mg plus O2 gives MgO. 4. Count the number of atoms on both sides of the equation. Reactant side, magnesium 1 atom, oxygen 2 atoms. Product side, magnesium 1 atom, oxygen 1 atom. 5. Balance the equation. The oxygen atoms in the equation are unbalanced. So, multiply the product side by 2. Mg plus O2 gives 2 MgO. 6. Now magnesium atoms are not balanced. So, multiply the magnesium atom reactant side by 2. 2Mg plus O2 gives 2MgO. 7. The equation is now balanced. Chemical equation for the reaction is 2Mg plus O2 gives 2MgO. Example 5.2. Write chemical equation for the reaction. Hydrogen combines with oxygen under conditions of high pressure to form water. Steps: formula of the reactants H2O2 in molecular form only. 2. Formula of the product H2O. H2 plus O2 gives H2O. 3. Count the number of atoms on both sides of the equation. Reactant side, hydrogen 2 atoms, oxygen 2 atoms. Product side, hydrogen 2 atoms, oxygen 1 atom. 4. Balance the equation. The oxygen atoms in the equation are not balanced. So, multiply the product side by 2. H2 plus O2 gives 2H2O. 5. Now hydrogen atoms are not balanced. So, multiply the hydrogen reactant side by 2. 2H2 plus O2 gives 2H2O. The equation is now balanced. 6. Chemical equation for the reaction is 2H2 plus O2 gives 2H2O. Significance of a chemical equation. 1. Chemical equation indicates the substances taking part in a chemical reaction and the products obtained. 2. It indicates the number of molecules of the reactants and products. 3. It enables to calculate the quantity of reactants and products by mass or volume. 4. It makes the study of chemistry universal. Chemical equation. Skeletal chemical equation. Chemical equations can be made more concise and useful if we use the symbols and chemical formulae instead of words for writing the reactants and products. Thus, a chemical equation is a symbolic notation that uses symbols and formulae instead of words to represent a chemical reaction. The word equation A on page 74 thus can be written as Mg plus O2 gives MgO. Now, if we compare the number of atoms of each element on the two sides of the arrow, the number of the atoms of oxygen is not same. Therefore, the equation is unbalanced because the total mass is not same on both sides of equation B. Such a chemical equation is called skeletal equation of the reaction. Similarly, skeletal equation for the reaction between zinc and dilute hydrochloric acid is given as Zn plus HCl gives ZnCl2 plus H2. Balanced chemical equation. A chemical equation in which the number of atoms of each element on the reactant side is equal to that on the product side is called a balanced chemical equation. Why a balanced chemical equation? The law of conservation of mass states that water can neither be created nor destroyed. Therefore, during a chemical reaction, the total mass of the reactants must be equal to the total mass of the products, and therefore, the number of atoms of each element in the reactants must be equal to that in the products. Such a chemical equation is called a balanced chemical equation. Need for balancing a chemical equation. A chemical equation needs to be balanced so as to make the number of the atoms of the reactants equal to the number of atoms of the products. According to the law of conservation of mass, matter can neither be created nor destroyed. Therefore, during a chemical reaction, the total mass of the reactants must be equal to the total mass of the products, and therefore, the number of atoms of each element in the reactants must be equal to that in the products. Such a chemical equation is called a balanced chemical equation. Balancing of a chemical equation. The act of equating the number of atoms of each element on both sides of a chemical equation is known as balancing of a chemical equation. Most of the unbalanced or skeletal equations can be balanced by following the steps given below. Steps: write the skeletal equation of the reaction. Now find out how many atoms of each type are on each side of the equation. You may make a table listing the number of each atom. For the left hand side LHS and for the right hand side RHS of the arrow. Now look for an element which is only one chemical on the RHS of the equation. Usually it is a good idea to balance H and O until you have done with other elements first. To balance that element, multiply the chemical species on the side which does not have enough atoms of that type by the number required to bring it up to the same as on the other side. This number is called coefficient. Then look for the next element or species that is not balanced and repeat the same procedure as in the above step. Repeat the procedure until atoms of all elements are balanced. Do not change the subscripts for the atoms in a chemical species because in doing so you will change it into a different species. In order to understand the application of the above method, let us take an example. Example 5.3. Give a balanced equation for the reaction where methane burns in air, O2, to form carbon dioxide and water. The word equation for this reaction is given as methane plus oxygen gives carbon dioxide plus water. Steps: 1. The skeletal equation of the reaction is CH4 plus O2 gives CO2 plus H2O. 2. The elements in the equation are C, H and O. Their respective numbers of atoms on the two sides of the equation are mentioned in the following table. 3. C is present both in CH4 and CO2, but it is already balanced. 4. Next, we start with H. We have 4H in CH4, but only 2H in H2O. Therefore, to balance H atoms, put coefficient 2 in front of H2O. That is, CH4 plus O2 gives CO2 plus 2H2O. 5. We have 2 atoms of O on LHS but 4 atoms of O on the RHS. Therefore, put coefficient 2 in front of O2 on the LHS, that is CH4 plus 2O2 gives CO2 plus 2H2O. Conclusively, we find that the number of atoms of each element on the two sides of the arrow is equal. Hence, the equation is balanced.
Information gathered from a chemical equation.
Through following facts, more information about the chemical reaction may be obtained from the chemical equation. Reaction catalyst conditions. Sometimes the reaction conditions such as temperature, pressure and presence of catalyst are indicated above and or below the arrow in the equation. For example, physical state of the reactants and products. The symbols like S for solid, L for liquid, G for gas and AQ for solution in water are written just after the formula to show the physical state of the reactants and products. The gas evolved may be indicated by an arrow pointing upwards just after downwards. The insoluble product, that is precipitate, is shown by an arrow pointing downwards. Nature of a chemical reaction. A reversible reaction, that is, reaction occurring both in the forward and backward directions, is represented by putting double-headed arrow between the reactants and the products. For example, concentration of reactants and products. This information is provided by putting the word dil or kong before the formula for a dilute or a concentrated solution of the reactants and the products. For example, characteristics of chemical equations. Chemical equation gives the number of atoms and or molecules of the reactants and the products of a chemical equation. It provides the names of various reactants and products of a chemical reaction. Chemical equation provides information about the relative volume of gaseous reactants and products. It gives number of moles of the reactants and the products. Limitations of chemical equations. When a substance is in the form of a solution, the chemical equation does not provide any information about its concentration. Chemical equation of the reaction does not give any actual idea about the rate of a reaction and how much time will be taken for the completion of the reaction. A chemical equation does not tell us about the feasibility of a reaction, that is, whether a reaction will take place or not. Fast track chapter at a glance. An element is a substance that cannot be split into simpler substances by chemical means or physical means. A compound is a substance that can be split into two or more substances by chemical means. A mixture is a substance containing more than one element or compound in any proportion. An atom of an element cannot be created or destroyed. Atoms are made up of electrons, protons, and neutrons. The atoms of an element with different mass numbers are called isotopes. Electrically charged atoms are called ions. A chemical reaction can be represented with the help of the symbols or the formulae of the elements and the compounds taking part in that reaction. This gives a chemical equation. A complete chemical equation represents the reactants, products, and their physical states symbolically. The substances that react with each other are called reactants and they are represented on the left-hand side of the equation. The substances that are formed as a result of the reaction are called products. They are represented on the right-hand side of the equation. A chemical equation needs to be balanced to make it follow the law of conservation of mass. The law of conservation of mass states that mass can neither be created nor destroyed. It can only be transformed from one form to another. A chemical equation gives both qualitative and quantitative information about reactants and Chapter 6